Hello, my name is Nur Izatul Dadilla and today I will talk about advanced gas-cooled reactor. Look, that's AGR. An advanced gas-cooled reactor or AGR is a type of nuclear reactor. It is designed and operated in the United Kingdom. Look, Papi, that is so big. The AGR represents the second generation of British gas-cooled reactors. It is developed from the earlier first-generation Magnus reactor design of gas-cooled reactor. In the UK, there are currently 7 AGR nuclear power stations, 5 in England and 2 in Scotland, with 2 operating reactors owned and operated by British Energy and are located and known as Dunstasby, Hartlepool, Heysham 1, Heysham 2, Hinkley Point B, Hudderston B, and Torness. AGR is using graphite as the neutron moderator and carbon dioxide as a coolant. This is the structure of AGR, which consists control rods, turbine generator, condenser, pump fuel elements, gas blower, graphite moderator, and boiler. The design of the AGR was such that final steam conditions at the boiler's top valve were identical to conventional coal-fired power stations. The mean temperature of the hot coolants leaving the reactor core was designed to be 648 degrees Celsius. The superheater outlet temperature and pressure were designed to be 2485 psi, which is equivalent to 170 bar and 543 degrees Celsius. The fuel is uranium dioxide pellets enriched to 2.5 to 3.5% in stainless steel tubes. It is designed to have a high thermal efficiency of about 41% better than pressurized water reactors, which has typical thermal efficiency of 34% due to higher coolant outlet temperature. And this is the example of AGR in Torness, United Kingdom. This is the General Nuclear Power Station. Like the other power stations, AGR has 5 basic components, and the first one is the reactor. The nuclear fission process will create heat in the reactor. The moderator in the reactor slows down the neutrons before they bombard on the fuel rods. This reactor has uranium-cooled fuel channels. A gas or a fluid will be pumped through the reactor, thus heating the fluid and cooling the reactor. The continued fission in the reactor will keep the reactor hot, so the heated fluid will pass to the heat exchanger, and this heat exchanger is the second basic component. Hot water is used to heat water, usually in the form of steam. The cooler fluid from the reactor, having passed through the heat exchanger, is piped back to the reactor. The very hot steam from the exchanger is piped to the steam turbine, which is the third basic component. And this steam turbine drives a generator to produce electricity. This is called alternator, and alternator is the fourth basic component. Electrical output of the alternator is delivered to a step-up transformer to transfer it over distance. And the last one, which is the fifth basic, is the condenser. The steam passes into condenser, where it turns back into water before being returned. Coal, oil, and nuclear power stations produce electricity in basically the same way. They use fuel to raise steam that turns a turbine to generate an electric current. In an advanced gas-cooled AGR station, a controlled chain reaction generates heat which turns water into steam. The steam then powers turbines, which in turn drive the electrical generators. At the heart of the reactor is a graphite core called the moderator. Moderator slows down the neutrons before they bombard on the fuel rods. Running vertically through this core are tubes containing uranium-cooled fuel channels. The moderator has a vital role to play as it slows down the neutrons released by the fuel so that they will interact with other uranium atoms and sustain the chain reaction. Within the pressure vessel, the boilers are connected to the inlet and outlet of the reactor by ducts. At the bottom of each boiler are large gas escalators which pump high-pressure carbon dioxide coolant gas through the graphite core and up the fuel channels, where the gas picks up the heat generated by the nuclear reaction. The gas, which is now very hot, will be routed through the top of the boiler back down to the gas escalator. As it passes through, it gives up its heat to the water in the boiler, forming superheated high-pressure steam which is piped away to drive the turbine. The superheated steam from the boilers is first piped to the high-pressure turbine where nozzles directed onto the blades. Then it will cause the turbine to rotate. The steam then returns the boiler to be reheated before passing to the intermediate pressure turbine. Then it will go to the low-pressure turbines. Having exhausted all its useful energy, the steam passes into the condenser where it turns back into water before being returned into the boiler. The condenser works by directing the steam over the surface of thousands of tubes containing cold filtered water pumped through the sea by circulating water pumps. When the cooling is complete in the water, its temperature rises by just a few degrees Celsius, then returned to the sea. The condensed water must be cleaned and heated before returning to the boilers. First, the water travels through a chemical plant to remove impurities and then through heaters where it is mixed with warm steam from the turbine to increase its temperature. Next, it is pumped into a large vessel called a deaerator to remove any gases before the feed pump sends it back to the boilers. The turbines drive a generator which consists of a large hydrogen-cooled electromagnet called a rotor. This rotor revolves at 3,000 revolutions per minute inside the stator, a water-cooled electrical winding. Electricity is produced in the windings of the stator at 23 kV by the revolving magnetic field of the rotor. And now let's see the comparisons with previous reactors. Like the Magnox, Chandu and RMBK reactors, and in contrast to the light water reactors, AGRs are designed to be refilled without being shut down first. This on-load refueling was an important part of the economic case for choosing the AUGR over other reactor types, and in 1965, allowed the Central Electricity Generating Board (CEGB) and the government to claim that the AGR would produce electricity cheaper than the best coal-fired power stations. The AGR was intended to be a superior British alternative to American light water reactor designs. It was promoted as a development of the operationally, if not economically, successful Magnox design, and was chosen from a multitude of competing British alternatives, which are the helium-cooled high-temperature reactor, the steam-generating heavy water reactor, and the fast breeder reactor, as well as the American light water pressurized and boiling water reactors, PWR and BWR, and Canadian Chandu designs. The CEB conducted a detailed economic appraisal of the competing designs and concluded that the AGR proposed for Dash B would generate the cheapest electricity, cheaper than any of the rival designs, and the best coal-fired stations. All AGR are expected to end operations by the end of 2023. Many member states are interested in and developing advanced high-temperature gas-cooled reactors (HTGRs) that use helium as a coolant. Such reactors can achieve very high fuel utilization rates and operate at high temperatures. They also produce process heat, which can be used for hydrogen production and low-temperature applications such as seawater desalination and district heating. After approximately 5 years, the fuel in the reactor can no longer maintain the chain reaction efficiently and must be replaced. To do this, a refueling machine removes and replaces fuel assemblies. These assemblies are then dismantled into individual parts. Most of the components are reused, but the fuel elements are sent to the cooling ponds.